Okay, let's jump straight in. Today we're looking at vThinker, interactive thinking with images.
Right. This paper is about getting large multimodal models, LMMs, to move beyond just looking at images. It wants them to actually, well, think with them actively.
Actively, yeah. So not just passive interpretation, but vision-centric thinking.
Exactly. And vThinker is this end-to-end reinforcement learning framework. It lets the LMM use code-driven visual tools to interact with the image as part of its reasoning.
And this whole system, vThinker, it really stands on two core ideas, two pillars, right?
That's right.
First, there's the Data Evolution Flywheel. It's basically an automated system for creating this massive data set, V-interaction 400K.
Yep. 400,000 examples, and it's designed specifically for diversity, quality, and increasing difficulty. It synthesizes the data itself.
Synthesizes it.
Yep.
Okay, and the second pillar.
That's the visual progressive training curriculum. This is key because it tackles a big LMM weakness-first visual perception. It uses point-level supervision to really nail down fine-grained details before it even gets to the interactive reasoning part with reinforcement learning.
So sharpen the vision first, then teach it how to act on what it sees. Makes sense.
Precisely.
And the results seem pretty clear-cut. vThinker is apparently outperforming strong baselines, even things like GPT-4o.
Consistently, yeah. Especially on this new benchmark they introduced, VTBench, which is designed for interaction and verified by experts.
It really sounds like a compelling argument that, visual reasoning needs a fundamental rethink.
It absolutely does. It's about moving from passive to active.
So let's unpack that a bit more, this need for interactive thinking. You mentioned active thinking with images, kind of like that old Aristotle idea.
The soul never thinks without an image, yeah. It's about making that link explicit for AI.
Because current LMMs, they're impressive, right? They generate these long chain of thought outputs.
Oh, absolutely. They can produce very elaborate text. But the problem is that reasoning often kind of floats free from the actual image.
Detaches from visual grounding, as the paper puts it.
Exactly. And that leads to visual hallucinations. The model starts describing things based on its language priors, what the text implies should be there, rather than what it's actually seeing.
Okay, I think I get that. It's like describing a complex machine without pointing at the specific parts as you go. You might know the theory, but you'll mess up the specifics.
That's a good analogy. The linguistic side is strong, but without the interaction, the grounding, and the visual details, it's prone to error, especially with spatial stuff.
And people have tried adding tools before, right? Like OpenAI's O3 or other systems. What was the limitation there?
Yeah, previous attempts often had issues. Maybe the range of visual actions was too narrow, or they needed really precise human input, like exact coordinates for where to draw a line.
Right, not very autonomous.
Not really. And some, like Deep Sketcher, had tools that were, well, too specific. Maybe good for adding lines and geometry problems, but not much else. They were tightly coupled to the task type.
So building a general-purpose tool system, that's the tricky part. How did vThinker avoid making its tools overly specialized? How did they actually get this interaction baked into the visual reasoning chain?
Well, they tackled it not just by designing tools, but by fundamentally changing how the training data was created. It was tool-centric right from the start.
Ah, okay.
And that brings us to the first big component of their post-training setup, this Data Evolution Flywheel, or DEF.
This is where they use a powerful LMM, maybe like a future GPT-5, not as the student, but as the teacher, or rather the creator.
Exactly. It's a shift from using the model as a solver to using it as a creator. This is pretty innovative.
Why is that shift so critical here?
Because for the kind of complex interactive reasoning vThinker aims for, you just can't find enough high-quality step-by-step labeled data out there. It doesn't exist at scale.
Right, nobody's manually annotated hundreds of thousands of interactive visual reasoning steps.
No way. So vThinker gets the LMM to generate Python code from scratch. This code doesn't just solve the problem, it actually renders the original images, it creates any needed diagrams like auxiliary lines, and it logs the entire reasoning path, the visual changes step by step.
Wow, okay, so instead of just labeling an image, the system is generating the visual state and the code that produces it. That's powerful.
It gives you incredible control. You can do really fine-grained edits via code, highlight tiny elements in a chemical structure, draw guidelines on a chart, annotate specific points, all synthesized.
And this DEF process, it builds up the huge V-interaction 400K dataset using three main principles: diversity, quality, and difficulty.
That's right. Those are the pillars of the flywheel.
So how does it ensure diversity? It sounds like just generating more might lead to repetition.
They use something called knowledge-driven evolution. It's this iterative loop. It goes back and forth between a knowledge system, K, and the set of visual tools, T. They kind of co-evolve. This process forces the generation of data points that are different, orthogonal, exploring new combinations of knowledge and tool use.
So it avoids getting stuck in a rut, generating the same kinds of problems.
Exactly. And it scales incredibly well. The paper mentions something like a 50x increase in dataset size from the initial seed after just 5 of these iterative cycles. That's serious growth for genuinely new interactive data.
Okay, that covers diversity. What about quality? How do they make sure all this generated data is actually correct and useful?
Through coordinated calibration. It's more than just checking the final answer. They have a data checker module. This checker looks at the answer's correctness, sure, but also whether the original generated image is valid, and crucially, whether the intermediate visual states the image edits made by the code are coherent and make sense together.
So it's checking if the visual steps logically follow each other.
Yes, it's a cross-modal consistency check. And here's a neat part. If the visual steps look coherent, but the final textual answer is wrong, they don't just toss the data. They have a repairer component that tries to reconstruct the question itself to match the valid visual reasoning path.
So it salvages the good visual logic by tweaking the prompt. That's smart. They're ensuring the text, the code, and the image sequence all line up.
Precisely. And finally, difficulty. They need to make sure the problems get progressively harder.
How do they manage that?
By systematically extending the required reasoning chain, the chain of thought length. They use 2 main strategies here. One is parallel extension, adding independent auxiliary steps that help solve the main problem. The other is sequential extension, where a new step relies directly on the result of the previous one.
So building complexity layer by layer.
Right. They cap it at a maximum depth of 3 steps to ensure real complexity without getting completely unwieldy.
Okay.
This careful layering makes the V-Interaction 400K dataset a really well-structured curriculum for training.
Okay, so they've built this amazing data set, the fuel. Now, how do they build the engine to actually use it effectively? That takes us to the second part, the Visual Progressive Training Curriculum, the VPTC.
Right. And the core idea behind the VPTC is tackling what they see as the LMM's Achilles heel.
Perception.
Perception, like just basic seeing.
Not just seeing, but accurately perceiving fine-grained visual details. Think points, intersections, specific anchor locations on objects. Even really powerful LMMs, linguistically, often stumble when you ask them to pinpoint exactly where something is. And that precision is vital if your tools are driven by code that needs coordinates or references.
I see. If the model can't reliably tell the code where to draw the line, the tool is useless.
Exactly. So stage 1 of the VPTC is all about perception alignment. They use a separate, smaller data set for this, the vPerception 40K data set.
And this data set is also synthesized. Yes, synthesized specifically for perception tasks. They designed it by considering 3 dimensions. The relationships between elements, like points on a line, angles, the number of elements in the image, samples are on a mean of 8, so it's not too sparse, and the underlying knowledge concepts involved.
So they're systematically training the model to locate things accurately in different contexts.
Pretty much. They use supervised fine-tuning, SFT here. It's about making the model hyper-accurate at localization, almost like a point-and-click expert. And they do this across different complexity levels. Just finding coordinates, surface level, identifying semantic features like a specific corner, semantic level, and combining location with some basic reasoning, integrated reasoning.
Okay, so nail the perception first. Then what?
Then stage 2, interactive reasoning alignment. This is where they bring in the big V-Interaction 400K dataset.
And how does the training work here?
It starts with what they call cold start SFT, basically using that big dataset to teach the model the basics of generating the Python code for interaction.
Giving it the initial capability.
Right. But then, crucially, they follow up with reinforcement learning, RL.
RL. How is that set up?
They use a framework called Group Relative Policy Optimization, or GRPO. The LMM operates inside a sandboxed environment. This sandbox is critical because it lets the model generate Python code, execute it safely to modify the image state, and then get feedback on the results, including the new visual state. It learns by doing, essentially.
Okay, and GRPO helps it explore different ways to use the tools effectively.
Yeah, GRPO is apparently good for encouraging robust exploration of different coding strategies, different ways to approach the visual interaction.
And the reward signal in RL is always tricky. How did they design the reward to encourage meaningful interaction, not just, messing around with the tools?
That's a really important point. They have a multi-part reward function. There's a component for accuracy, one for formatting, like is the output structured correctly, and one for tool usage.
Okay. But how do they stop it from just, say, drawing random circles to get the tool use reward?
That's the clever bit. The overall reward structure is designed specifically to prevent that. The formula looks something like total reward, accuracy reward, plus lambda 1 formatting reward, plus lambda 2 indicator tool reward. The key is that indicator function. It means the tool usage reward is only added if the final answer is actually correct and if at least one tool was used.
Ah, so no points for using tools unless you get the right answer.
Exactly. You can't just fiddle with the image for the sake of it. The interaction has to be productive, leading to the correct solution. It forces the model towards efficient, necessary visual steps.
That makes a lot of sense. Okay, so they've done this very careful data generation and this progressive training. How did they evaluate if it actually worked, this new benchmark, VTBench?
Right, VTBench. It's
Yeah.
specifically built for this. It's not like standard vision benchmarks. Every task in VTBench requires visual interaction
Requires it. How did they ensure that?
through expert verification. For every single problem instance, they had multiple human experts review it. At least 3 out of 5 experts had to agree that, yes, you absolutely need to interact with the image job, draw something, label something to solve this problem correctly.
That's a high bar, so it's really testing the core capability they trained for.
Definitely. And they structured the benchmark evaluation along the lines of their training curriculum. Perception tasks, then instruction-guided interaction, like draw a line between these 2 points, and finally, full interactive reasoning, where the model has to figure out the interaction itself.
And the results. You mentioned earlier that standard models struggled.
Staggeringly so, especially on the interaction parts. Looking at the results table in the paper, for instruction-guided interaction, GPT-4o scored only 2.3% accuracy.
Right, 2.3% for GPT-4o, that's surprisingly low.
It is. And Qwen 2.5 VL7B, another strong baseline, only got 8.8%. It really highlights that perception bottleneck. These models might be smart linguistically, but precise visual interaction is a massive weakness.
Wow, okay, so that basically proves their point about needing that focused perception training. It's not just a minor issue, it's a fundamental gap.
It seems so. It's like an architectural blindness to fine-grained localization. But VThinker, the 7D parameter version they tested, it showed huge improvements.
Yeah.
Specifically, in that instruction-guided interaction domain, it was 25.8 percentage points better than Qwen 2.5 VL7B.
Plus 25.8%. That's a massive jump. It really shows the specialized training paid off in terms of interactive ability.
Absolutely. It demonstrates a much stronger capability for, well, actionable interactive thinking.
Were there any qualitative examples that stood out? Like, how does VThinker behave differently?
Yeah, the paper mentions it shows stable and quite fine-grained visual editing. But interestingly, even on some tasks that didn't strictly require drawing or editing, maybe a simple math problem based on an image, VThinker would sometimes proactively annotate the image.
Proactively, like adding its own notes.
Kind of, yeah. To clarify its intermediate reasoning steps, like a human using scratch paper, drawing diagrams to make sure they're on the right track. It's externalizing its thought process visually.
But it's interesting. It suggests a different kind of reasoning process is emerging.
It does. And they also did some analysis showing that during the RL phase, VThinker explores a wider range of possible solution paths, suggesting it's better at adapting and finding good visual strategies.
And did they check if both parts of the training were needed, the perception part and the RL part?
Yes, the Ablation studies confirmed it. If they remove the initial perception alignment stage, performance drops significantly. Same if they remove the RL stage. It shows that the whole visual progressive training curriculum perception first, then interactive RL is necessary to get those big gains. The full sequence works together.
And does this specialized skill translate? Does it help on more general tasks?
Apparently, yes. They tested VThinker on broader reasoning benchmarks like Math Vision and found consistent improvements there too, about a 6.3% accuracy gain.
So the interactive thinking paradigm isn't just for niche tasks. It seems to transfer and help with general visual reasoning.
That's the implication. Learning to interact robustly seems to deepen its overall visual understanding.
So wrapping up, VThinker seems like a really solid framework. It tackles interactive thinking head-on with this clever data synthesis flywheel and the progressive training.
It definitely provides a strong proof of concept for bridging visual grounding with active, code-driven tool use.
Are there limitations mentioned? Where does it go from here?
The main one they acknowledge is scale, which isn't too surprising for such a complex system. Computational limits meant the current VThinker models aren't enormous. So performance might still lag on tasks that are extremely knowledge-heavy or require understanding very specific niche domains where just having massive parameter counts helps a lot.
Right. So the framework is sound, but scaling it up further is the next obvious step.
Absolutely. And the paper kind of ends on this thought, that work like vThinker really pushes us as researchers to rethink things.
Yeah.
We need to reconsider how we even create data, maybe shifting more towards models as creators like the DF does. And also, we need to reconsider what the upper limits of model reasoning even are.
Pushing the boundaries of what thinking with images actually means.
Exactly. It's moving towards AI that interacts with the visual world in a way that feels much more natural, much more human-like. This isn't just about seeing anymore. It's about doing things within the image to help figure stuff out.